Well, welcome back to our course, Computer Organization and Architecture. We're continuing our process of working through various types of memory and now getting into input and output. And just as a reminder, in terms of the context of what we're doing for the second major section in our textbook, we're going through the various aspects of the computer system. Gave a nice top-level view of computer function and interconnection. We talked about various types of memory hierarchy, cache, internal memory, and external memory. And now with this lecture, we're going to be talking about input and output. So this will be an interesting chapter as all of them, but let's get into this. And so first of all, let's have a reminder, start out with a summary, and then we'll come back to this chart of what we're going to cover. And so I/O, input, output, we'll be talking about the various ways in which that's done. External devices, input and output modules, programmed I/O, interrupt-driven I/O, direct memory access, or DMA. And so these are various ways of how you can tap on the shoulder of your computer and get into it. You can have direct cache access. You can have I/O channels and processors, external interconnection standards, and finally, we'll talk about the IBM Z Enterprise EC12 I/O structure. So a variety of things that we'll get a chance to get exposed to in the survey of input and output. So first, here's a generic model of an I/O module. And so an I/O module is required. Thus, the module has two major functions, as we can see in this figure, the interface to the processor and memory via the system bus or central switch, and the interface to one or more peripheral devices by tailored data links. So those are the things that we'll get a chance to get some insight into here as we go. We begin this chapter with a brief discussion of external devices, followed by an overview of the structure and function of the I/O module. Then we will look at various ways in which the I/O function can be performed in cooperation with a processor and memory. So the input, output, processor, and memory, that's the von Neumann architecture. The internal I/O interface. Finally, we examine the external I/O interface between the I/O module and the outside world. So as we're talking now about external devices, the I/O operations are accomplished through a wide assortment of external devices that provide a means of exchanging data between the external environment and the computer. An external device attaches to the computer by a link to an I/O module. So you can think back to figure 8.1 we just were showing. The link is used to exchange control, status, and data between the I/O modules and the external device. An external device connected to an I/O module is often referred to as a peripheral device or simply a peripheral. We can broadly classify external devices into three categories: human readable, which is suitable for communicating with the computer user; machine readable, which is suitable for communicating with equipment; and communication, which is suitable for communicating with remote devices. Examples of human readable devices in video display terminals, VDTs, and printers. Examples of machine readable devices are magnetic disk and tape systems, and sensors and actuators such are used in a robotics application. Note that we are viewing disk and tape systems as I/O devices in this chapter, whereas in chapter 7, we view them as a memory device. From a functional point of view, these devices are part of the memory hierarchy, and their use is appropriately discussed in chapter 7. From a structural point of view, these devices are controlled by I/O modules and are hence to be considered in this chapter. So we're getting a chance to see it from two different points of view. Communication devices allow a computer to exchange data with a remote device, which may be a human readable device such as a terminal, a machine readable device, or even another computer. So here we have a block diagram of an external device. In very general terms, the nature of an external device is indicated here in figure 8.2. The interface to the I/O module is in the form of control data and status signals. Control signals determine the function that the device will perform, such as send data to an I/O module, input or read, accept data from an I/O module, output or write, report status, or perform some control function particular to the device. For example, position a disk head. Data are in the form of a set of bits to be sent to or received from the I/O module. Status signals indicate the state of the device. Examples are ready or not ready to show whether the device is ready for data transfer. The control logic associated with the device controls the device's operation in response to direction from the I/O module. The transducer converts data from electrical to other forms of energy during output and from other forms to electrical during input. Typically, a buffer is associated with the transducer to temporarily hold data being transferred between the I/O module and the external environment. A buffer size of 8 to 16 bits is common for serial devices, whereas a block-oriented devices such as disk drives, controllers may have much larger buffers. The interface between the I/O module and the external device will be examined in section 8.7. The interface between the external device and the environment is beyond the scope of this book, this lecture, or this course, but several brief examples are given here so we can get a chance to get some perspective from a survey point of view. A disk drive contains electronics for exchanging data, control, and status signals with an I/O module, plus the electronics for controlling the disk read-write mechanism. In a fixed head disk, the transducer is capable of converting between the magnetic patterns on the moving disk surface and bits in the device's buffer. So here was some aspects of what we're seeing here in figure 8.2. A moving head disk must also be able to cause a disk arm to move radially in and out across the disk's surface. The most common means of computer user interface is a keyboard and monitor arrangement. The user provides input to the keyboard. This input is then transmitted to the computer and may also be displayed on the monitor. In addition, the monitor displays data provided by the computer. The basic unit of exchange is the character. Associated with each character is a code. Typically 7 or 8 bits is in length. The most commonly used text code is the International Reference Alphabet, IRA. Each character in this code is represented by a unique 7-bit binary code, thus 128 different characters can be represented. Characters are of 2 types, printable and control. Printable characters are the alphabetic, numeric, and special characters that can be printed on paper or displayed on a screen. Some of the control characters have to do with controlling the printing or displaying of characters. An example is a carriage return. Other control characters are concerned with the communication procedure. And so Appendix D has more details if you would like to check that out. For keyboard input, when the user depresses a key, this generates an electronic signal that is interpreted by the transducer in the keyboard and translates into the bit pattern of the corresponding IRA code. The bit pattern is then transmitted to the I/O module and the computer. At the computer, the text can be stored in the same IRA code. On output, IRA code characters are transmitted to the external device from the I/O module. The transducer at the device interprets this code and sends the required electronic signals to the output device, either to the display, the indicated character, or perform the requested control function. Another type of code is ASCII, and that may be a term that some of you may have heard, but here we're talking about the IRA. So another example of a code that things can be laid out in. So let's talk about the I/O functions. The major functions or requirements for an I/O module fall into the following categories: control and timing, which coordinates the flow of traffic between the internal resources and external resources; the processor communication, which involves command decoding, data status reporting, and address recognition; the device communication, which involves command, status information, and data buffering, which performs the needed buffering operations to balance device and memory speed; and error detection, with the detection reports transmission errors. During any period of time, the processor may communicate with one or more external devices in unpredictable patterns depending on the program's need for I/O. The internal resources, such as the main memory and the system bus, must be shared among a number of activities, including data I/O. Thus, the I/O function includes a control and timing requirement to coordinate the flow of the traffic between the internal resources and external devices. For example, the control of the transfer of data from an external device to the processor might involve the following sequence of steps. One, the processor interrogates the I/O module to check the status of the attached device. Two, the I/O module returns the device status. Three, if the device is operational and ready to transmit, the processor requests the transfer of data by means of a command to the I/O module. Four, the I/O module obtains a unit of data, for example, 8 or 16 bits, from the external device. Five, the data are transferred from the I/O module to the processor. If the system employs a bus, then each of the interactions between the processor and the I/O module involves one or more bus arbitrations. The preceding simplified scenario also illustrates that the I/O module must communicate with the processor and with the external devices. Processor communication involves the following: command decoding. The I/O module accepts commands from the processor, typically sent as signals on the control bus. For example, an I/O module for a disk drive might accept the following commands: read sector, write sector, seek track number, and scan record ID. The latter two commands are included, each include a parameter that is sent on the data bus. Next, the data are exchanged between the processor and the I/O module over the data bus. Status reporting. Because peripherals are so slow, it is important to know the status of the I/O modules. For example, if an I/O module is asked to send data to the processor as in a read, it may not be ready to do so because it is still working on the previous I/O command. This fact can be reported with a status signal. Common status signals are busy and ready. There may also be signals to report various error conditions. Address recognition: just as each word of memory has an address, so does each I/O device. Thus, the I/O module must recognize one unique address for each peripheral it controls. On the other hand, the I/O module must be able to perform device communication. This communication involves commands, status information, and data. So this is something from figure 8.2 if you want to check back and look at that. An essential task of the I/O module is data buffering. The need for this function is apparent from figure 2.1 if you want to go back to chapter 2 to look over that. Whereas the transfer rate into and out of the main memory or the processor is quite high, the rate is orders of magnitude lower for many peripheral devices and covers a wide range. Data comes from the main memory, are sent to an I/O module in rapid bursts. The data are buffered in the I/O module and then sent to the peripheral device at its data rate. In the opposite direction, data are buffered so as not to tie up the memory in a slow transfer operation. Thus, the I/O module must be able to operate at both device and memory speeds. Similarly, if the I/O device operates at a rate higher than the memory access rate, then the I/O module performs the needed buffering operation. Finally, an I/O module is often responsible for error detection for subsequently reporting errors to the processor. One class of errors include mechanical and electrical malfunctions reported by the device, for example, a paper jam, bad disk track. Another class consists of unintentional changes to the bit pattern as it is transmitted from the device to I/O module. Some form of error detecting code is often used to detect transmission errors. A simple example is the use of a parity bit on each character of data. For example, the IRA code occupies 7 bits of a byte. The 8th bit is set so that the total number of ones in the byte is even. So that would be even parity, or odd, that would be odd parity. When a byte is received, the I/O module checks the parity to determine whether an error has occurred. So here's a block diagram of an I/O module. An I/O module I/O modules vary considerably in complexity and the number of external devices that they control. We will attempt only a very general description here. One specific device, the Intel 8255A, is described in section 8.4, and so we'll see that in a little while. So in this figure 8.3, it provides a general block diagram of an I/O module. The module connects to the rest of the computer through a set of signal lines, that is, system bus lines. Data transferred to and from the module are buffered in one or more data registers. There may also be one or more status registers that provide current status information. A status register may also function as a control register to accept detailed control information from the processor. The logic within the module interacts with the processor via a set of control lines. The processor uses the control lines to issue commands to the I/O module. Some of the control lines may be used by the I/O module, for example, for arbitration and status signals. The module must also be able to recognize and generate addresses associated with the devices it controls. Each I/O module has a unique address, or if it controls more than one external device, a unique set of addresses. Finally, the I/O module contains logics specific to the interface with each device that it controls. An I/O module functions to allow the processor to view a wide range of devices in a simple-minded way. There is a spectrum of capabilities that may be provided. The I/O module may hide the details of timing, formats, and the electromagnetics of an external device so that the processor can function in terms of simple read and write commands, and possibly open and close file commands in the simplest form. The I/O module may still leave much of the work of controlling a device, that is, rewind a tape, visible to the processor. An I/O module that takes on most of the detailed processing burden, presenting a high-level interface to the processor, is usually referred to as an I/O channel or an I/O processor. An I/O module that is quite primitive and requires detailed control is usually referred to as an I/O controller or device controller. I/O controllers are commonly seen on microcomputers, whereas I/O channels are used on mainframes. In what follows, we will use the generic term I/O module when no confusion results, and we will use a more specific term where necessary. Okay, let's talk about programmed I/O. Three techniques are possible for I/O operations with programmed I/O. Data are exchanged between the processor and the I/O module. The processor executes a program that gives it direct control of the I/O operation, including sensing device status, sending a read or write command, and transferring the data. When the processor issues a command to the I/O module, it must wait until the I/O operation is complete. If the processor is faster than the I/O module, this is wasteful of processor time. With interrupt-driven I/O, the processor issues an I/O command, continues to execute other instructions, and is interrupted by the I/O module when the latter has completed its work. With both programmed and interrupt I/O, the processor is responsible for extracting data from main memory for output and storing data in main memory for input. The alternative is known as direct memory access, or DMA. In this mode, the I/O module and main memory exchange data directly without processor involvement. So thus we had a nice overview of each one of these three scenarios. Here in this table, 8.1, where we are showing I/O techniques, and it indicates a relationship among these three techniques. In this section, we explore program I/O, interrupt I/O, and DMA, and so this is what we'll be covering in the next two sections, and so just keep that in mind. So let's talk about I/O commands. To execute an I/O related instruction, the processor issues an address, specifies a particular I/O module, an external device, and an I/O command. There are four types of I/O commands that an I/O module may receive when it is addressed by a processor. First, control, used to activate a peripheral and tell it what to do. For example, a magnetic tape unit may be instructed to rewind or to move forward one record. These commands are tailored to a particular type of peripheral device. Next, we have test. It is used to test the various status conditions associated with an I/O module and its peripherals. The processor will want to know that the peripheral of interest is powered on and available for use. It will also want to know if the most recent I/O operation is completed and if any errors occurred. Next, we have read, and it causes the I/O module to obtain an item of data from the peripheral and place it in the internal buffer. It's depicted as a data register in figure 8.3, and the processor can then obtain the data item by requesting the I/O module place it on the data bus. Finally, we have write, and it causes the I/O module to take an item of data, a byte or a word, from the data bus and subsequently transmit that data item to the peripheral. So here, figure 8.4, we see three techniques for input of a block of data. And it gives an example of a use of program ID to I/O to read in a block of data from a peripheral device, for example, a record from tape, into memory. Data are read in one word, for example, 18 bits at a time. For each word that is read in, the processor must remain in a status checking cycle until it determines that the word is available in the I/O module's data register. This flow chart highlights the main disadvantages of this technique. It is a time-consuming process that keeps the processor busy needlessly. And so this is an example of what we would want to be trying to move away from. So for I/O instructions, with programmed I/O, there is a close correspondence between I/O related instructions from the processor fetches from memory and the I/O commands that the processor issues to an I/O module to execute the instructions. That is, the instructions are easily mapped into I/O commands, and there is often simple one-to-one relationships. The form of an instruction depends on the way in which the external devices are addressed. Typically, there may be many I/O devices connected through an I/O module to the system. Each device is given a unique identifier or address. When the processor issues an I/O command, the command contains the address of the desired device. Thus, each I/O module must interpret the address lines to determine if the command is for itself. When the processor, main memory, and I/O share a common bus, two modes of addressing are possible: memory, mapping, and isolated. With memory mapped I/O, there is a single address space for memory locations and I/O devices. The processor treats the status and data registers of the I/O modules as memory locations and uses the same machine instructions to assess both memory and I/O devices. So, for example, with 10 address lines, a combined total of 2 to the 10 or 1024 memory locations, and I/O addresses can be supported in any combination. With memory mapped I/O, a single read line and a single write line are needed on the bus. Alternatively, the bus may be equipped with a memory read and write plus input and output command lines. Now the command lines specifies whether the address refers to a memory location or an I/O device. The full range of addresses may be available for both. Again, with 10 address lines, that the system may now support both 1024 memory locations and 1024 I/O addresses because the address space for I/O is isolated from that of the memory. This is referred to as isolated I/O. Okay, here is an I/O mapping summary. The memory mapped I/O devices a memory share and address space. I/O looks just like memory read I/O. No specific commands for I/O, and a large section of the memory access commands are available. So that's for memory mapped, and for isolated I/O, separate address spaces. You need to have I/O or memory select lines and special commands for I/O, and there is a limited set associated with that. Okay, moving on. Here we have figure 8.5, memory mapped and isolated I/O. So this figure contrasts these two programmed I/O techniques. Figure 8.5a. So that's what we have on the upper 2/3 of this chart here, of this figure, shows how the interface for a simple input device such as a terminal keyboard might appear to a programmer using memory mapped I/O. Assume a 10-bit address with a 512-bit memory with location 0 to 511 and up to 512 I/O addresses, locations 512 to 1023. The two addresses are dedicated to keyboard input from a particular terminal. Address 516 refers to the data register address, and 517 refers to the status register, which also function as a control register for receiving process commands. The program shown will read 1 byte of data from the keyboard into an accumulator register in the processor. Note that the processor loops until the data byte is available. With isolated I/O, shown in figure 585b down at the bottom, the I/O ports are available only by special I/O commands, which activate the I/O command lines on the bus. For most types of processors, there is a relatively large set of different instructions for referencing memory. If isolated I/O is used, there are only a few I/O instructions. Thus, an advantage of memory mapped I/O is that this large repertoire of instructions can be used, allowing more efficient programming. A disadvantage is that valuable memory address space is used up. Both memory mapped and isolated I/O are in common use. So basically, with the input and output, one feature that we have is it can act as a translator. The language, the way the things that a processor is expecting to see, the way things are physically in the memory, the way that it actually translates from a specific peripheral and puts it into a format that is usable for a processor. All these kind of things, and we're getting into some details here as we're talking about these various approaches. So next, let's talk about interrupt-driven I/O. The problem with programmed I/O is that the processor has to wait a long time for the I/O module of concern to be ready for either reception or transmission of data. And this historically is the way that it was done. You had polling. The processor, while waiting, must repeatedly interrogate the status of the I/O module. As a result, the level of the performance of an entire system is severely degraded. As an alternative is for the processor to issue an I/O command to a module, then go on to do some other useful work. The I/O module then will interrupt the processor to request service when it is ready to exchange data with the processor. The processor then executes the data transfer as before, and then resumes its former processing. So it's able to multitask. Let us now consider how this works. First, from the point of view of an I/O module, for input, the I/O module receives a read command from the processor. The I/O module then proceeds to read data in from an associated peripheral. Once the data are in the module's data register, the module signals an interrupt to the processor over a control line. The module then waits until its data are requested by the processor. When the request is made, the module places its data on the data bus and is then ready for another I/O operation. From the processor's point of view, the action for input is as follows. The processor issues a read command. It then goes off and does something else. For example, the processor may be working on several different programs at the same time. At the end of each instruction cycle, the processor checks for interrupts. That's something you can go back to figure 3.9 in chapter 3 if you'd like. When the interrupt from the I/O module occurs, the processor saves the context, for example, the program counter and the processor registers of the current program and processes that and then it saves data of the current program and processes the interrupt. So it breaks and then it does what it's meant to do in that break. In this case, the processor reads a word of data from the I/O module and it stores it in memory. It then restores the content of the program it was working on or some other program and resumes execution. Figure 8.4b shows the use of an interrupt I/O for reading in a block of data. Compare this with figure 8.4a. Interrupt I/O is more efficient than programmed I/O because it eliminates needless waiting. However, interrupt I/O still consumes a lot of processor time because every word of data that goes from the memory to the I/O module or from the I/O module to the memory must pass through the processor. Okay, well, let's discuss some simple interrupt processing. So let's consider a role of the processor in interrupt-driven I/O in more detail. The occurrence of an interrupt triggers a number of events, both in the processor hardware and in software. Figure 8.6, what we're showing here, shows a typical sequence when an I/O device completes an I/O operation. The following sequence of hardware events occurs. 1, the device issues an interrupt signal to the processor. 2, the processor finishes execution of the current instruction before responding to the interrupt as indicated in figure 3.9. Once again, go back to chapter 3 if you want to see that. The processor tests for an interrupt, determines that there is one, and sends an acknowledgement signal to the device that issues the interrupt. The acknowledgement allows the device to remove its interrupt signal. 4, the processor now needs to prepare to transfer control to the interrupt routine. To begin, it needs to save information needed to resume the current program at the point of interruption. The minimum information required are A, the status of the processor, which is contained in the register called the program status word, PSW, and B, the location of the next instruction to be executed, which is contained in the program counter. These can be pushed onto the system control stack. 5, the computer now loads the program counter with the entry location of the interrupt handling program that will respond to this interrupt. Depending on the computer architecture and operating system design, there may be a single program, one program for each type of interrupt, or one program for each device and each type of interrupt. If there is more than one interrupt handling routine, the processor must determine which one to invoke. This information may have been included in the original interrupt signal, or the processor may have to issue a request for the device that issued the interrupt to get a response that contained the needed information. Here we see the changes in memory and registers for an interrupt. And so once the program counter has been loaded, the processor proceeds to the next instruction cycle, which begins with the instruction fetch. Because the instruction fetch is determined by the contents of the program counter, the result is that control is transferred to the interrupt handler program. The execution of the program results in the following operation. So continuing on, number 6, we were talking about this before. So at this point, the program counter and PSW relating to the interrupt program have been saved on the system stack. However, there is other information that is considered part of the quote state of the executing program. In particular, the contents of the processor registers need to be saved because these registers may be used by the interrupt handler. So all of these values plus any other state information needs to be saved. Typically, the interrupt handler will begin by saving the contents of all the registers on the stack. Figure 8.7a shows a simple example. In this case, a user program is interrupted after the instruction at location N. The contents of all of the registers plus the address of the next instruction, N+1, are pushed onto the stack. The stack pointer is updated to point to the new top of the stack, and the program counter is updated to point to the beginning of the interrupt service routine. Then number 7, the interrupt handler next processes the interrupt. This includes an examination of status information related to the IO operation or other events that cause an interrupt. It may also involve sending additional commands or acknowledgements to the IO device. 8, when the interrupt processing is complete, the saved register values are retrieved from the stack and restored to the registers. You can see this in figure 8.7b on the right over here. And then number 9, the final act is to restore the PSW and program counter values from the stack. As a result, the next instruction to be executed will be from the previously interrupted program. Note that it's important to save all the state information about the interrupted program for later resumption. This is because the interrupt is not a routine call from the program. Rather, the interrupt can occur at any time and therefore at any point in the execution of a user program. Its occurrence is unpredictable. Indeed, as we will see in the next chapter, the two programs may not have anything in common and may belong to different users. So let's talk about design issues. 2 design issues arise in implementing the interrupt IO. First, because there will almost invariably be multiple IO modules. How does a processor determine which device issues the interrupt? And second, if multiple interrupts have occurred, how does a processor decide which one to process? So it can get a little bit complicated. And so we need to have some kind of an algorithm, some type of a methodology to go ahead and do that. So let's talk about the device identification. There's 4 general categories and techniques in common use. So let us consider the device identification for those scenarios. First, we have the multiple interrupt lines, the software polling, the daisy chain, that is hardware polling and vectored, and bus arbitration or vectored. The most straightforward approach to the problem is to provide a multiple interrupt lines between the processor and the IO modules. However, it is impractical to dedicate more than a few bus lines or processor pins to interrupt lines. Consequently, Even if multiple lines are used, it is likely that each line will have multiple I/O modules attached to it. Thus, one of the other three techniques must be used in each line. An alternative is the software pool. When the processor detects an interrupt, it branches to an interrupt service routine whose job is to pull each of the I/O modules to determine which module caused the interrupt. The pull could be in the form of a separate command line, for example, a test or I/O. In this case, the processor raises the test I/O and places the address of a particular I/O module on the address lines. The I/O module responds positively if it sets the interrupt. Alternatively, each I/O module could contain an addressable status register. The processor then reads the status register of each I/O module to identify the interrupting module. Once the correct module is identified, the processor branches to a device service routine specific to that device. The disadvantage of the software pool is that it is time consuming. A more efficient technique is to use a daisy chain. Now we're getting into the next one here. Which provides in effect a hardware pull. An example of a daisy chain configuration is shown in figure 3.26. You can go back to chapter 3 to see that. For interrupts, all I/O modules share a common interrupt request line. The interrupt acknowledge line is daisy chained through the modules. When the processor senses an interrupt, it sends out the interrupt acknowledge. This signal propagates through a series of I/O modules until it gets to the requesting module. The requesting module typically responds by placing a word on the data lines. The word is referred to as a vector and is either the address of the I/O module or some other unique identifier. In each case, the processor uses the vector as a pointer to the appropriate device service routine. This avoids the need to execute a general interrupt service routine first. This technique is called a vectored interrupt. There's another technique that makes use of a vector interrupt, and that is the bus arbitration. With bus arbitration, an I/O module must first gain control of the bus before it can raise the interrupt request line. Thus, only one module can raise the line at a time. When the processor detects the interrupt, it responds on the interrupt acknowledge line. The request module then places its vector on the data line. Well, let's look at the use of the 82C59A interrupt controller. The Intel 8386 provides a single interrupt request, INTR, and a single interrupt acknowledge, INTA, line to allow the 8386 to handle a variety of devices and priority structures. It is usually configured with an external interrupt arbiter, the 82C59A. External devices are connected to the 82C59A, which in turn connects to the 8386. Figure 8.8, which we're showing here, shows the use of the 82C59A to connect multiple I/O modules for the 8386. A single 82C59A can handle up to 8 modules. If control for more than 8 modules is required, a cascade arrangement can be used to handle up to 64 modules. The 82C59A's sole responsibility is the management of interrupts. It accepts interrupt requests from attached modules, determines which interrupt has the highest priority, and then signals the processor by raising the INTR line. The processor acknowledges with the INTA line. This prompts the 82C59A to place the appropriate vector information on the data bus. The processor can then proceed to process the interrupt and communicate directly with the I/O modules to read or write data. The 82C59A is programmable. The 8386 determines a priority scheme to be used by setting a control word in the 82C59A. The following interrupt modes are possible. First, fully nested, the interrupt request an ordered in priority from 0, that is IR0, through 7, that is IR7. Next is rotating. In some applications, a number of interrupt devices are of equal priority. In this mode of the device, after being serviced, receive the lowest priority in the group. And finally, special mask. This allows the processor to inhibit interrupts from certain devices. So here we're seeing a figure of the Intel 8255A programmable peripheral interface. And so this is an example of an I/O module used for programmed I/O and interrupt-driven I/O. We consider the Intel 8255A programmable peripheral interface. The 8255A is a single-chip general-purpose I/O module originally designed for use with the Intel 8386 processor. It has since been cloned by other manufacturers and is a widely used peripheral controller chip. Its uses include as a controller for the simple I/O devices for microprocessors and embedded systems, including microcontroller systems. In this figure 8.9, it shows a general block diagram plus the pin and assignment for the 40-pin package in which it is housed. The right side of the block diagram of figure 8.9a is the external interface of the 8255A. The 24 I/O lines are divided into three 8-bit groups, A, B, and C. Each group can function as an 8-bit I/O port, thus providing connections for 3 peripheral devices. In addition, group C is subdivided into 4-bit groups, that is CA and CB, which may be used in conjunction with A and B I/O ports. Configured in this manner, group C lines carry control and status signals. The left side of the block diagram is the internal interface to the microprocessor system bus and includes an 8-bit bidirectional data bus, D0 through D7, used to transfer data between the microprocessor and the I/O ports and to transfer control information. The processor controls the 8255A by means of an 8-bit control register in the processor. The processor can set the value of the control registers to specify a variety of operating modes and configurations. From the processor point of view, there is a control port and the control register bits are set in the processor and then sent to the control port over lines D0 through D7. Next, let's dig into the Intel 8255A control word. Thus, when the processor sets both an A1 and A2 to 1, the 8255A interrupts the 8-bit value on the data bus as a control word. When the processor transfers an 8-bit control word with line D7 set to 1, which we're seeing in this figure, figure 810A, and so the control word is used to configure the operating mode of the 24 I/O lines. The 3 modes are mode 0. This is the basic I/O module mode. The 3 groups of 8 external lines function as 3 8-bit I/O ports. Each port can be designated as an input or output. Data may only be sent to a port if the port is defined as output, and data may only be read from a port if the port is set to input. That's mode 0, and then mode 1. In this mode, ports A and B can be configured as either input or output, and lines from port C serve as control lines for A and B. The control signals serve 2 principal purposes: handshaking, and interrupt requests. Handshaking is a simple timing mechanism. One control line is used by a sender as a data ready line to indicate when the data are present on the IO data lines, and another line is used by the receiver as acknowledge, indicating that the data has been read and the data lines may be cleared. Another line may be designated as an interrupt request line and tied back to the system bus. And then for mode 2, this is a bidirectional mode. In this mode, port A can be configured as either the input or the output lines for a bidirectional traffic on port B, with the port B lines providing the opposite direction. Again, the port C lines are used for control signals. When the processor sets D7 to 0, which is figure 810B, the control word is used to program the bit values of port C individually. This feature is rarely used. So we see A over here on the left side and B on the right side if you hadn't followed that with while I was giving that description. Here in figure 811, we're showing the keyboard display interface to the 8255A. Because the 8255A is programmable via control register, it can be used to control a variety of simple peripheral devices. So figure 811, this figure illustrates its use to control a keyboard display terminal. The keyboard provides 8 bits of input. 2 of these bits, shift and control, have special meaning to the keyboard handling program. However, in the processor, sorry, let's say that 2 of these bits, shift and control, have special meaning to the keyboard handling program. However, in the processor, this interpretation is transparent to the 8255A, which simply accepts the 8 bits of data and presents them on the system data bus. The 2 handshaking lines are provided for use with the keyboard. The display is also linked by an 8-bit data port. Again, 2 of the bits have special meaning that are transparent to the 8255A. In addition to 2 handshaking lines, the 2 lines provide additional control function. So just to finish a few other comments, so we're seeing an example where there's a mostly an input device. Inputs going from the keyboard. So for the IO, sometimes you have things say like a cap key lock or something, but mostly that's just fairly modest, that things that might return. And then you have a mostly an output device going to the display. A little bit that might be coming back is giving some information about the monitor and stuff like that. So fairly flexible device that we're seeing here, and we're seeing a type of IO configuration that's fairly common, that must exist for us to have some effective computing and engagement with that capability. So what are the drawbacks of programmed and interrupt-driven IO? Interrupt-driven IO, although more efficient than simply programmed IO, still requires the active intervention of the processor to transfer data between memory and an IO module, and any data transfer must traverse a path through the processor. Thus, both these forms of IO suffer from 2 inherent drawbacks. The IO transfer rate is limited by the speed with which the processor can test and service a device. So everything is being routed through the processor. The processor is tied up to manage an IO transfer. A number of instructions must be executed for each IO transfer. So this referred to figure 8.5. There is somewhat of a trade-off between these 2 drawbacks. Consider the transfer of a block of data. Using simple programmed IO, the processor is dedicated to the task of IO and can move data at a rather high rate. at the cost of doing nothing else. Interrupt IO frees up the processor to do to some extent at the expense of the IO transfer rate. Nevertheless, both methods have an adverse impact on both processor activity and IO transfer. When large volumes of data are to be moved, a more efficient technique is required in which is direct memory access. So here is a typical block diagram for DMA, direct memory access. DMA involves an additional module on the system bus. The DMA module, as we're shown here in figure 812, is capable of mimicking the processor and indeed of taking over the control of the system from the processor. So you're offloading things from the processor. It needs to do this to transfer data to and from memory over the system bus. For this purpose, the DMA module must use the bus only when the processor does not need it, or it must force a processor to suspend operation temporarily. The later technique is more common and is referred to cycle stealing because the DMA module in effect steals a bus cycle. When the processor wishes to read or write a block of data, it issues a command to the DMA module by sending to the DMA module the following information. Whether a read or write is requested using the read or write control line between the processor and the DMA module, the address of the IO device involved communicated on the data lines, and the starting location in memory to read from or write to communicated on the data lines and stored by the DMA module in the address lines. The number of words to be read or written, again committed via the data lines and stored in the data count register, and the processor then continues with other work. If the delegated task IO operations it has delegated the IO operation to the DMA module and probably quite happy about it. The DMA module transfers the entire block of data one word at a time directly to or from memory without going through the processor. When the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and at the end of the transfer. And so you can refer back to figure 8.4c if you like. So here we're showing the DMA and interrupt breakpoints during an instruction cycle. So we're showing when the instruction cycle, shows where in the instruction cycle the processor may be suspended. In each case, the processor is suspended just before it needs to use the bus. The DMA module then transfers one word and returns control to the processor. Note that this is not an interrupt. The processor does not save a context and do something else. Rather, the processor pauses for one bus cycle. The overall effect is to cause the processor to execute more slowly. Nevertheless, for multiple word IO transfer, DMA is far more efficient than interrupt-driven or programmed IO. So now we got a good, better sense of each one of these scenarios. Now let's talk about an alternative DMA configurations, plural. The DMA mechanism may be configured in a variety of ways. Some possibilities are shown in this figure, 8.14. In the first example, all modules share the same system bus. The DMA module acts as a surrogate processor using programmed IO to exchange the data between memory and an IO module through the DMA module. This configuration, while it may be inexpensive, is clearly inefficient. As with processor-controlled IO, each transfer of the word consumes 2 bus cycles. The number of required bus cycles can be cut substantially by integrating the DMA and IO functions. As figure 8.14b indicates, this means that there is a path between the DMA module and one or more of the IO modules that does not include the system bus. The DMA logic may actually be part of an IO module, or it may be a separate module that controls one or more I/O modules. This concept can be taken one step further by connecting I/O modules to the DMA module using an I/O bus. That's what's shown in figure 814C. This reduces the number of I/O interfaces in the DMA module to one and provides for an easy expandable configuration. In both these cases, that is figures 814B and C, the system bus that the DMA module shares with the processor and memory is used by the DMA module only to exchange data with memory. The exchange of the data between the DMA and the I/O modules takes off the exchange of the data between the DMA and the I/O modules takes place off the system bus. So once again, we're getting some interesting ways to offload the processor, and that is so we see some various ways of how we can be improving performance with these kind of strategies. Next, let's look at the 8237 DMA usage of system bus. The Intel 8237A DMA controller interfaces to a 80 times 86 and 80 x86 family of processors, so 286, 386, 46, etc., processors to DMA memories to configure a DMA capability. Figure 815 indicates the location of the DMA module. When the DMA module needs to be used, the system buses, the data address control, to transfer data, it sends a signal called hold to the processor. The processor responds with the HLDA, hold acknowledge signal, indicating that the DMA module can use the buses. For example, if the DMA module is to transfer a block of data from memory to a disk, it will do the following. One, the peripheral device, such as a disk controller, will request the services of DMA by pulling DREC, the DMA request, high. The DMA, there's number two, the DMA will put a high on the HRQ, the hold request, signaling the CPU hold CPU through its hold pin that it needs to use the buses. Three, the CPU will finish its present bus cycle, not necessarily the present instruction, and respond to the DMA request by putting high on the HDLA, the hold acknowledge, thus telling the 8237 DMA that it can go ahead and use the buses to perform the task. Hold must remain active high as long as the DMA is performing its task. Number four, DMA will activate the DAC, DMA acknowledge, which tells the peripheral device that it will start to transfer the data. Five, the DMA starts to transfer the data from memory to peripherals by putting the address of the first byte of the block on the address bus and activated MEMR, MEMR, thereby reading the byte from memory into the data bus. It then activates IOW to write it to the peripheral. The DMA decrements the counter and decrements the address pointer and repeats this process until the count reaches 0 and the task is finished. Number six, after the DMA has finished its jobs, it deactivates the HRQ, signaling the CPU that it can regain control of over its buses. So there is a little bit of contention that has to be resolved, but here we're just introducing the possibilities of how all those can work. Now let's talk about flyby DMA controller. When the DMA is using the buses to transfer data, the processor is idle. Similarly, when the processor is using the bus, the DMA is idle. The 8237 DMA is known as a flyby DMA controller. This means that the data being moved from one location to another does not pass through the DMA chip and is not stored in the DMA chip. Therefore, the DMA can only transfer data between an IO port and memory address, but not between 2 I/O ports or 2 memory locations. However, as explained subsequently, the DMA chip can perform a memory-to-memory transfer via register. The 8237 contains 4 DMA channels that can be programmed independently, and any one of the channels may be active at the moment. These channels are numbered 0, 1, 2, and 3. Here is a table for the Intel 8237A registers. So the 8237 has a set of 5 control/command registers to program control DMA operations over one of the channels. That's what we're seeing in this table, 8.2. So first of all, the command, the processor loads this register to control the operator of the DMA. D0 enables a memory-to-memory transfer in which the channel 0 is used to transfer a byte into the 8237 temporary register, and channel 1 is used to transfer the byte from the register to the memory. When memory-to-memory is enabled, D1 can be used to disable increment-decrement on channel 0 so that a fixed value can be written into the block of memory. D2 enables or disables the DMA. Next, we have the status register. The processor reads this register to determine DMA status. Bits D0 through D3 are used to indicate if channels 0 through 3 have reached their TC, that is their terminal count. Bits D4 through D7 are used by the processor to determine if any channel has a DMA request pending. Then we have the mode. The processor sets this register to determine the mode of the operation of the bits. Bits D0 and D1 are used to select a channel. The other bits select various operation modes for the selection channels. Bits D2 and D3 determine if a transfer is from an I/O device to memory, that is for write, or from memory to I/O, that is read, or verify operation. If D4 is set, then the memory address register and the count register are reloaded with their original values at the end of the DMA data transfer. Bits D6 and D7 determines the way in which the 8237 is used. In single mode, a single byte of data is transferred. Block and demand mode are used for a block transfer, with the demand mode allowing for premature ending of the transfer. Cascade mode allows multiple 8237s to be cascade to expand the number of channels to more than 4. Next, we have the single mask. The processor sets the register. This register, bits D0 and D1 select the channel. Bit D2 clears or sets the mask for that channel. It is through this register that the direct input of the specific channel can be masked, disabled, or unmasked, enabled. While the command register can be used to disable the whole DMA chip, the single mask register allows a programmer to disable or enable a specific channel. Finally, we have the all mask. This register is similar to the single mask register, except that all 4 channels can be masked or unmasked with one write operation. In addition, the 8237A has 8 data registers, 1 memory address register, and 1 count register for each channel. The processor sets these registers to indicate the location of size of many memory to be affected by the transfers. Okay, let's next talk about direct cache access, or DCA. DMA has proven an effective means of enhancing performance of I/O with peripheral devices and network I/O traffic. However, the dramatic increase in data rates for network I/O, DMA is not able to scale to meet the increased demand. The demand is coming primarily from the widespread deployment of 10 gigabits and 100 gigabit Ethernet switches to handle massive amounts of data transfers to and from database servers and other high performance systems. A secondary but increasingly important source is traffic coming from Wi-Fi in the gigabit range. Network Wi-Fi devices that handle 3.2 gigabits per second and 6.76 gigabits per second are becoming widely available and producing demands on the enterprise systems. In this section, we will show how enabling the I/O function to have direct access to the cache can enhance performance, a technique known as direct cache access. Throughout this section, we are concerned only with the cache that is closest to the main memory, referred to as the last cache level, the last level cache. In some systems, this will be L3 caches, and others it'll be L4. We saw some enterprise level type of capabilities that they had an L4 cache, but we'll just stick with what we're talking about here. To begin, we describe the way in which contemporary multi-core systems use on-chip shared cache to enhance DMA performance. This approach involves enabling the DMA function to have direct access to the next level cache. Next, we examine cache-related performance issues that manifest when high-speed network traffic is processed. From there, we look at the several different strategies for DCA that are designated to enhance network protocol processing performance. Finally, this section describes a DCA approach implemented by Intel, referred to as direct data I/O. Here is a figure for the Xeon E5 2600/4600 chip architecture. The Intel Xeon is Intel's high-end, high-performance processor family used in servers, high-performance workstations, and supercomputers. Many of the members of the Xeon family use a ring interconnect system, as illustrated here in this figure. The E5 2600/4600 can be configured with up to 8 cores on a single chip. Each core has a dedicated L1 and L2 cache. There's a shared L3 cache of up to 20 megabytes. The L3 cache is divided into slices, one associated with each core, although each core can address the entire cache. Further, each slice has its own cache pipeline, so that request can be sent in parallel to the slices. The bidirectional high-speed ring interconnect links cores, last level cache, PCIEs, and integrated memory controllers, the IMCs. In essence, the ring operates as follows. One, each component that attaches to the bidirectional ring, QPI, PCIe, L3 cache, L2 cache, is considered a ring agent and implements ring agent logic. Number two, the ring agents cooperate via a distributed protocol to request and allocate access to the ring in the form of time slots. Number three, when an agent has data to send, it chooses the ring direction that results in the shortest path to the destination and transmits when a scheduling slot is available. The ring architecture provides good performance and scales well for multi-cores up to a point. For systems with greater number of cores, multiple rings are used, with each ring supporting some of the cores. In traditional DMA operations, data is exchanged between many memory and an I/O device by means of a system interconnect structure, such as a bus, ring, or QPI point-to-point matrix. So for example, if the Xeon E5 2600/4600 uses a traditional DMA technique, output would proceed as follows. An I/O driver running on a core would send an I/O command to the I/O controller labeled PCIe in figure 816 with the location and size of the buffer in main memory containing the data to be transferred. the I/O controller issues a read request that is routed to the memory controller hub, MCH, which accesses the data on a DDR3 memory and puts it on the system ring for delivery to the I/O controller. The L3 cache is not involved in this transaction, and one or more off-chip memory reads are required. Similarly, for input, data arrives from the I/O controller and is delivered over the system ring to the MCH and written out to main memory. The MCH must also invalidate any L3 cache lines corresponding to the updated memory locations. In this case, one or more off-chip memory writes are required. Further, if an application wants to access the new data, a main memory read is required. With the availability of large amounts of last level cache, a more efficient technique is possible and used by the Xeon E5 2600/4600. For output, when the I/O controller issues a read request, the MCH first checks to see if the data is on the L3 cache. This is likely to be the case if an application has recently written data into the memory block to be output. In this case, the MCH directs the data from the L3 cache to the I/O controller. No main memory access are needed. However, it also causes the data to be evicted from the cache. That is, the act of reading by the I/O device causes the data to be evicted. Thus, the I/O operation proceeds efficiently because it does not require a main access. But if an application does need that data in the future, it must read back into the L3 cache from the main memory. The input operation on the Xeon E5 2600/4600 operates as described in the previous paragraph. The L3 cache is not involved. Thus, the performance improvement involves only output operations. A final point, although the output transfer is directly from the cache to the I/O controller, the term direct cache access is not used for this feature. Rather, the term is reserved for I/O protocol application as described in the remainder of this section. Okay, let's continue with cache-related performance issues. Network traffic is transmitted in the form of sequence of protocol blocks called packets or protocol data units. The lowest or link level protocol is typically Ethernet, so that each arriving and departing block of data consists of an Ethernet packet containing as payload the higher level protocol packet. The higher level protocol are usually the Internet Protocol IP operating on top of the Ethernet and the Transmit Control Protocol TCP operating on the top of the IP. Accordingly, the Ethernet payload consists of a block of data with a TCP header and an IP header. For ongoing data, the Ethernet packets are formed in a peripheral component such as an I/O controller or network interface controller, NIC. Similarly, the incoming traffic, the I/O controller strips off the Ethernet information and delivers the TCP IP packets from the host CPU. For both outgoing and incoming traffic, the core, main memory, and cache are all involved. In a DMA scheme, when an application wishes to transmit data, it places the data in an application assigned buffer in main memory. The core transfers this to a system buffer in main memory and creates the necessary TCP and IP headers, which are also buffered in system memory. The packet is then picked up via DMA for transfer via the NIC. This activity engages not only main memory, but also the cache. For incoming traffic, similar traffic transfers between systems and application buffers are required. When large volumes of protocol traffic are processed, two factors in the scenario degrade performance. First, the core consumes valuable clock cycles in copying data between the system and application buffers. And second, because memory speeds have not kept up with the CPU speeds, the core loses time waiting on memory reads and writes. In the traditional way of processing protocol traffic, the cache does not help because the data and protocol headers are constantly changing, and thus the cache must constantly be updated. Okay, let's talk about packet traffic steps to clarify the performance issues and to explain the benefit of DCA as a way of improving performance. Let us look at the processing of protocol traffic in more detail for incoming traffic. In general terms, the following steps occur. Number one, packet arrival. The NIC receives an incoming Ethernet packet. The NIC processes and strips off the Ethernet control information. This includes doing an error detection calculation. The remaining TCP IP packet is then transferred to the system DMA module, which generally is part of the NIC. The NIC also creates a packet descriptor with information about the packet, such as the buffer location and memory. Number two, DMA. The DMA module transfers data, including the packet descriptor to main memory. It must also invalidate the corresponding cache lines, if any. Number three, the NIC interrupts the host. After a number of packets have been transferred, the NIC issues an interrupt to the host processor. Number four, it retrieves descriptors and headers. The core processes the interrupts, invokes an interrupt handling procedure, which reads the descriptor and header of the received packets. Number five, the cache miss occurs. Because this is a new data coming in, the cache lines corresponding to the system buffer contain that the new data are invalidated. Thus, the core must stall to read the data from main memory into cache and then to the core registers. Number six, the header is processed. The protocol software executes on the core to analyze the contents of the TCP and IP headers. This will likely include accessing a transmit control block, a TCP, which contains context information related to TCP. The TCP access may or may not trigger a cache miss, necessitating a main memory access. And number seven, the payload transfer. The data portion of the packet is transferred from the system buffer to the appropriate application buffer. A similar sequence of steps occurs for outgoing packet traffic, but there are some differences that affect how the cache is managed for outgoing traffic. The following steps occur. Number one, the packet transfer is requested. When an application has a block of data to transfer to a remote system, it places the data in an application buffer and alerts the operating system with some type of system call. Number two, the packet is created. The operating system invokes the TCP/IP process to create the TCP/IP packet for transmission. The TCP/IP process accesses the TCP, which may involve a cache miss, and creates the appropriate headers. It also creates the data from the application buffer and then places the completed packet, the header, plus the data in a system buffer. Note that the data that is written into the system buffer also exists in the cache. The TCP/IP process also creates a packet descriptor. This is placed in memory shared with the DMA module. Number three, the output operation is invoked. This uses a device driver program to signal the DMA module that output is ready for the NIC. Number four, the DMA transfer. The DMA module reads the packet descriptor, and then a DMA transfer is performed from main memory or the last level cache to the NIC. Note that the DMA transfers invalidates the cache line in cache, even if the case of the read by the DMA module. If the line is modified, this causes a write back. The core does not do the invalidates. The invalidates happens when the DMA module reads the data. Number 5, the NIC signals completion. After the transfer is complete, the NIC signals of the driver on the core that the originated the send signal. And number 6, the driver frees buffer. So once the driver receives the completion notice, it frees up the buffer space for reuse. The core must also invalidate the cache lines containing the buffer data. As we can see, the network I/O involves a number of accesses to cache and main memory and the movement of data between an application buffer and a system buffer. The heavily involvement of main memory becomes a bottleneck as both core and network performance outstrips gains in memory access time. So let's talk about direct cache accessing strategies. Several strategies have been proposed for making more efficient use of caches for networked I/O, with a general term direct cache access applied to all of these strategies. The simplest strategy is one that was implemented as a prototype on a number of Intel Xeon processors between 2006 and 2010. This form of DCA applies only to incoming network traffic. The DCA function in the memory controller sends a prefetch hint to the core as soon as the data is available in system memory. This enables the core to prefetch the data packet from the system buffer, thus avoiding cache misses and the associated waste of core cycles. While this simple form of DCA does provide some improvement, much more substantial gain can be realized by avoiding the system buffer and main memory altogether. For this specific function or protocol processing, note that the packet and packet descriptor information are accessed only once in the system buffer by the core. For incoming packets, the core reads the data from the buffer and transfers the packet payload to the application buffer. It has no need to access the data in the system buffer again. Similarly, for outgoing packets, once the core has placed the data in the system buffer, it has no need to access the data again. Suppose, therefore, that the I/O system were equipped not only with the capability of direct accessing main memory, but also of accessing the cache both for input and out operations. Then it would be possible to use the last level cache instead of the main memory to buffer packets and descriptors of incoming and outgoing packets. This last approach, which is a true DCA, was proposed in some of the literature that the text refers to. It has also been described as a cache injection. A version of this more complicated form of DCA is implemented in Intel's Xeon processor line, referred to as the direct data I/O. So let's look at a comparison of DMA and DDIO. Intel Direct Data I/O, or DDIO, is implemented on all of the Xeon E5 family of processors. Its operation is best explained with a side-by-side comparison of transfers with and without DDIO. First, we look at the case of the packet arriving at the NIC from the network. Figure 817A shows the steps involved for a DMA operation. The NIC initiates a memory write 1. Then the NIC invalidates the cache lines corresponding to the system buffer 2. Next, the DMA operation is performed, depositing the packet directly into the main memory 3. Finally, after the appropriate core receives a DMA interrupt signal, the core has read the packet data from memory through the cache 4. Before discussing the process of incoming packets using DDIO, we need to summarize the discussion of cache write policy from Chapter 5 and introduce a new technique. For the following discussion, there are issues related to cache coherency that arise in a multiprocessor or multi-core environment. These are discussed in Chapter 19, but the details need not concern us here. Recall There are two techniques for dealing with an update in a cache line. Write through is the first one and write back is the second one. Write through, all write operations are made to main memory as well as to the cache, ensuring that the main memory is always valid. Any other core cache module can monitor traffic to main memory to maintain consistency with its own local cache. The other is the write back. It updates are made only in the cache. When an update occurs, a dirty bit associated with the line is sent. Then when a block is replaced in it, they're written back to the main memory if and only if the dirty bit is set. DDIO uses the write back strategy in the L3 cache. A cache write operations may encounter a cache miss, which is dealt with by one of the two strategies. First, the write allocate, the required line is loaded into the cache from the main memory. Then the line in the cache is updated by the cache operation. This scheme is typically used when the write back with the write back method. Then we have the non-write allocate. The block is modified directly in main memory. No change is made to the cache. This scheme is typically used with the write-through method. With the above in mind, we can describe the DDIO strategy for inbound transfers initiated by the NIC. If there is a cache hit, if there is a cache hit, the cache line is updated, but not main memory. This is simply the write back strategy for a cache hit. The Intel literature refers to this as a write update. If there is a cache miss, number two, if there is a cache miss, the write operation occurs to a line in the cache that will not be written back to the main memory. Subsequent write updates the cache line, again with no references to main memory or no future action that writes this data to main memory. The Intel documentation refers to this as a write allocate, which unfortunately is not the same meaning for the term in the general cache literature. The DDIO strategy is effective for a network protocol application because the incoming data need not be retained for future use. The protocol application is going to write the data to an application buffer, and there is no need to temporarily store it in a system buffer. So figure 817B shows the operation for DDIO input. The NIC initiates a memory write 1. Then the NIC invalidates the cache line corresponding to the system buffer and deposits the incoming data in the cache. 2. Finally, after the appropriate core receives a DCA interrupt signal, the core can read the packet data from the cache. 3. Finally, for figure 817C, it shows the steps involved for a DMA operation for outbound packet traffic transmission. TCP/IP protocol handlers executing on the core reads data in from an application buffer and writes it out to the system buffer. These data access operations result in cache misses and cause data to be read from memory and into L3 cache. 1. When the NIC receives notification for starting a transmit operation, it reads the data from the L3 cache and transmits it. 2. The cache accessed by the NIC causes the data to be evicted from the cache and writes back to main memory. 3. And then finally, in figure 817D, it shows the steps involved for a DDIO operation for packet transmission. The TCP/IP protocol handler creates the packet to be transmitted and stores it in allocated space in the L3 cache, but not in the main memory. 2. The read operation initiated by the NIC is satisfied by the data from the cache without causing eviction to main memory. It shows it should be clear from these slides, side-by-side slides, the comparison that DDIO is more efficient than DMA for both incoming and outgoing packets, and is therefore better to keep up with a high packet traffic rate. Let's talk about the evolution of the I/O function. As computer systems have evolved, there have been a pattern of increasing complexity and sophistication of individual components. Nowhere is this more evident in the I/O function. We have already seen parts of that evolution. The evolution steps can be summarized as follows. The CPU directly controls a peripheral device. This is seen as simple microprocessor controlled devices. Number two, a controller or I/O module is added. The CPU uses programmed I/O without interrupts. With this step, the CPU becomes somewhat divorced from the specific details of external device interfaces. Number three, the same configuration as step two is used, but now interrupts are employed. The CPU need not specify need not spend time waiting for the I/O operation to be performed, thus increasing efficiency. Number four, the I/O module is given direct access to memory via DMA, direct memory access. It can now move a block of data to or from memory without involving the CPU, except at the beginning and end of the transfer. Number five, the I/O module is enhanced to become a processor in its own right with a specialized instruction set tailored for I/O. The CPU directs the I/O processor to execute an I/O program in memory. The I/O processor fetches and executes these instructions without CPU intervention. This allows the CPU to specify a sequence of I/O activities and to be interrupted only when the entire sequence has been performed. And finally, number six, the I/O module has a local memory of its own, is in fact a computer in its own right. With this architecture, a large set of I/O devices can be controlled with a minimal CPU involvement. A common use for such an architecture has been to control communication and interactive terminals. The I/O processor takes care of most of the tasks involved in controlling the terminals. An I/O process proceeds along this evolutionary path. More and more of the I/O function is performed without the CPU involvement. The CPU is increasingly relieved of I/O related tasks, improving performance. With the last two steps, that is 5 and 6 that we talked about in this list, a major change occurs with the introduction of the concept of an I/O module capable of executing a program. For steps 5, the I/O module is often referred to as an I/O channel. For step 6, the I/O processor is often used. However, both terms are on occasion applied to both situations. In what follows, we will use the term I/O channel. Next, let's talk about the I/O channel architecture. The I/O channel represents an extension of the DMA concept. An I/O channel has the ability to execute I/O instructions, which gives it complete control over I/O operations. In a computer system with such devices, the CPU does not execute I/O instructions. Such instructions are stored in main memory to be executed by a special purpose processor in the I/O channel itself. Thus, the CPU initiates an I/O transfer by instructing the I/O channel to execute a program in memory. The program will specify the device or devices, the area of memory for storage, priority, and actors to be taken for certain error conditions. The I/O channel follows these instructions and controls the data transfer. Two types of I/O channels are common, as illustrated in the figure we're showing here in figure 818. So first, a selector channel controls the multiple high-speed devices, and at any one time is dedicated to the transfer of data with one of those devices. Thus, an I/O channel selects one device and affects the data transfer. Each device or a small set of devices is handled by a controller or I/O module. That is much like the I/O modules we have been discussing. Thus, the I/O channel serves in place of the CPU in controlling these I/O controllers. A multiplexer channel can handle I/O with multiple devices at the same time. For low-speed devices, a byte multiplexer accepts or transmit characters as fast as possible to multiple devices. For example, the resultant characters stream from 3 devices with different rates and individual streams. So something that I believe everyone is familiar with is Universal Service Bus, USB. It's a widely used for peripheral connections. It is a default interface for slower speed devices, such as keyboards and pointing devices, but it also is commonly used for high-speed I/O, including printers, disk drivers, and network adapters. USB has gone through multiple generations. The first version, USB 1.0, defined as a low-speed data rate of 1.5 megabits per second and a full-speed data rate of 12 megabits per second. USB 2.0 provided a data rate of 480 megabits per second. USB 3 included a new higher speed bus called the super speed in parallel with the USB 2.0 bus. The signal speed of the super speed is 5 gigabits per second, but due to signaling overhead, the usable data rate is up to 4 megabits per second. The most recent specification is USB 3.1, which uses a faster transfer mode called super speed. This transfer mode achieves a signal rate of 10 gigabits per second and a theoretical usable data rate of 9.7 gigabits per second. A USB system is controlled by a root host controller, which attaches to devices to create a local network with a hierarchy tree topology. Next, we have the FireWire serial bus. It was developed as an alternative to small computer system interface, the SCSI interface, to be used on smaller systems such as a personal computer, workstations, and servers. The objective was to meet the increasing demands for high I/O rates on these systems while avoiding the bulky and expensive I/O capacity channel technologies developed for mainframes and supercomputer systems. The result is the IEEE standard 1394, a high-performance serial bus commonly known as FireWire. FireWire uses a daisy chain configuration up to 63 devices connected off a single port. Moreover, up to 1022 FireWire buses can be interconnected using a bridge, enabling a system to support as many peripherals as required. FireWire provides for what is known as hot plugging, which makes it possible to connect and disconnect peripherals without having to power the computer system down or reconfigure the system. Also, FireWire provides for automatic configuration. It is not necessary to manually set device IDs or be concerned with the relative position of devices. With FireWire, there are no terminations and no system automatically performs a configuration function to assign addresses. A FireWire bus need not be a strict daisy chain, rather a tree structure configuration is possible. An important feature of the FireWire standard is that it specifies a set of 3 layers of protocols to standardize the way in which the host system interacts with the peripheral devices over the serial bus. The physical layer defines the transmission media that are permissible under FireWire and the electrical and signaling characteristics of each. Data rates from 25 megabits per second to 3.2 gigabits per second are defined. The link layer describes the transmission of data in the packets. The transaction layer defines a request response protocol that hides the lower layer details of FireWire from applications. Next, let's consider SCSI. SCSI is a common standard for connecting peripheral devices disks, modems, printers, etc., to small and medium-sized computers. Although SCSI has evolved to higher data rates, it has lost popularity to such competitors as USB and FireWire in smaller systems. However, high-speed versions of SCSI remain popular for mass memory support on enterprise systems. For example, the IBM Z Enterprise EC12 and the other IBM mainframes offer support for SCSI, and a number of Seagate hard drive systems use SCSI. The physical organization of SCSI is a shared bus which can support up to 16 or 32 devices depending on the generation of the standard. The bus provides for parallel transmission rather than serial, with a bus width of 16 bits on earlier generations and 32 bits on later generations. Speeds range from 5 megabits per second on the original SCSI 1 specification to 116 megabits per second on SCSI 3. Finally, there's the Thunderbolt, the most recent and fastest peripheral connecting technology to become available for general purpose use is the Thunderbolt, developed by Intel with collaboration from Apple. One Thunderbolt cable can manage the work previously required of multiple cables. The technology combines data, video, audio, and power into a single high-speed connection for peripherals such as hard drives. That is, you can have it for hard drives, for RAID. Remember, that's redundant array of independent disk arrays, video capture boxes, and network interfaces. It provides up to a 10 gigabits per second throughput in each direction and up to 10 watts of power to connect peripherals. InfiniBand is an I/O specification aimed at the high-end server market. The first version of the specification was released in early 2001 and has attracted numerous vendors. For example, IBM Z Enterprise series of mainframes has relied heavily on InfiniBand for a number of years. The standard describes an architecture and specification for data flow among processors and intelligent I/O devices. InfiniBand has become a popular interface for storage area networking and other large storage configurations. In essence, InfiniBand enables servers, remote storage, and other network devices to be attached in a central fabric of switches and links. The switch-based architecture can connect up to 64,000 servers, storage systems, and network devices. Then we have the PCI Express and SATA. We've been exposed to PCI Express previously, but let's go ahead and talk about these now. The PCI Express is a high-speed bus system for connecting peripherals on a wide variety of types of systems. Chapter 3 discussed the PCI Express in detail, and you might want to recall that or go back to Chapter 3 and review. The serial ATA or SATA or Serial Advanced Technology Attachment is an interface for disk storage systems. It provides data rates up to 6 gigabits per second with a maximum per device of 300 megabits per second. SATA is widely used in desktop computers and in industrial and embedded applications. Ethernet is a predominant wired networking technology used in homes, offices, and data centers, enterprises, and wide area networks. And Ethernet has evolved to support data rates up to 100 gigabits per second and distances from a few meters to tens of kilometers. It has become essential for supporting personal computers, workstations, servers, and massive data storage devices in organizations large and small. Ethernet began as an experiment bus-based 3 megabit per second with a bus system. All of the attached devices, such as PCs, connect to a common coaxial cable, much like residential cable TV systems. The first commercially available Ethernet and its first version of IEEE 802.3 were bus-based systems operating at 10 megabits per second. As technology has advanced, Ethernet has moved from bus-based to switch-based, and the data rates has periodically increased by an order of magnitude. With a switch-based system, there is a central switch with all the devices connecting directly to a switch. Currently, Ethernet's systems are available at speeds up to 100 gigabits per second. Here's a brief chronology. 1983, 10 megabits per second. 95, 100 megabits per second. 98, 1 gigabits per second. 2003, 10 gigabits per second. And 2010, there was a 40 gigabits per second and 100 gigabits per second. We have Wi-Fi, which is quite common, as I'm sure you all are familiar with. Wi-Fi is a predominant wireless internet access technology used in homes, offices, and public spaces. Wi-Fi is in the home now connects computers, tablets, smartphones, and a host of electronic devices such as video cameras, TVs, and thermostats. Wi-Fi in the enterprise has become an essential means of enhancing worker productivity and worker effectiveness. And public Wi-Fi hotspots have expanded dramatically to provide free internet access in most public spaces. As the technology of antennas, wireless transmission techniques, and wireless protocols designs have evolved, the IEEE 802.11 committee has been able to introduce standards for new versions of Wi-Fi at even higher speeds. Once the standard is issued, industry quickly develops the products. Here is a brief chronology starting with the original standard, which was simply called IEEE 802.11 and shows the maximum data rate for each version. So 802.11, 2 megabits per second. 802.11a, 54 megabits per second. That was in 1999. 802.11b, 1999, 11 megabits per second. 802.11n, which was also proposed in 1999, had a data rate of 600 megabits per second. 802.11g, proposed in 2003, had 54 megabits per second. 802.11ad, proposed in 2012, had 6.76 megabits per second. And also we have an 802.11ac, proposed in 2014, has 3.2 gigabits per second. Okay, here we have a figure of the IBM Z30 IO channel structure. The Z13 has a dedicated IO subsystem that maintains all IO operations, completely offloading the processor and memory burden from the main processors. Figure 819 that we're showing here shows the logical structure of the IO subsystem of the 168 core processors. Up to 24 of these can be dedicated for IO use, creating a 46-channel subsystem, CSS. Each CSS is made up of the following elements. The system assistant processor, SAP. The SAP is a core processor configured for IO operation. Its role is to offload IO operations and manage channels with the IO operations queues. It relieves the other processors of all IO tasks, allowing them to be dedicated to application logic. There's also the hardware system area, HSA. The HSA is reserved part of the system memory containing the IO configuration. It is used by SAPs. A fixed amount of 32 gigabytes is reserved, which is not part of the customer purchase memory. This provides a greater configuration flexibility and higher availability by eliminating planned and pre-planned outages. Next, we have logical partitions. A logical partition is a form of virtual machine, which is in essence a logical processor defined at the operating system level. Each CSS supports up to 16 logical partitions. Next, we have subchannels. A subchannel appears in a program as a logical device and contains the information required to perform an I/O operation. One subchannel exists for each I/O device, addressable by the CSS. A subchannel is used by the channel subsystem code running on a partition to pass an I/O request to the channel subsystem. A subchannel is assigned for each device defined to the logical partition. Up to 196K subchannels are supported per CSS. The channel path. A channel path is the single interface between a channel subsystem and one or more control units. Via a channel, commands in the data are sent across a channel path to perform I/O requests. Each CSS can have up to 256 channels. For channels, channels are small processors that communicate with the I/O control units, the CUs. They maintain the data transfer between memory and the external devices. This elaborate structure enables the mainframe to maintain a massive number of I/O devices and communication links. All I/O processing is offloaded from the application server and processors, enhancing performance. The channel subsystem processors are somewhat general in configuration, enabling them to manage a whole wide variety of I/O devices and to keep up with the evolving requirements. The channel processors are specifically programmed for I/O control units to which they interface. Okay, well, let's go ahead and finish up this lecture here. This is the last chart before our summary. And so here we have an IBM Z13 I/O system structure. So to explain the I/O system organization, we need to first briefly explain the physical layout of the Z13. The system has the following characteristics. It weighs 2567 kilograms. Its width is 1.847 meters. Its depth is 1.806 meters, and its height is 2.146 meters. Not exactly a laptop, in other words. The system consists of two large bays called frames bolted together that house various components of the Z13. The A frame houses 4 processor drawers, interconnects via Ethernet, and one PCI I/O drawer, which contains I/O hardware, including multiplexers and channels. The A frame also includes 2 support servers used by a system manager for platform management, battery backup, and a cooling unit. It can use either water or air. The Z frame houses up to 4 I/O drawers, which can be combined, a combination of PCI drawers and customer selected I/O drawers. The Z frame also includes battery backup and a keyboard display tray, which contains the keyboards and the displays that are connected to the support servers. With this background, we can now show a typical configuration of the Z13 I/O system structure as we're showing in this figure 820. Each Z11 processor drawer supports 2 types of internals, internal to the A and Z frames, I/O infrastructures, PCI Express, and InfiniBand. Each processor drawer includes a card containing the channel controller, which provides a connectivity to the I/O drawers. These channels controllers are referred to as fanouts. The InfiniBand connectors from the processor book to the I/O drawers are via host channel adapter HCA fanout, which has InfiniBand links to InfiniBand multiplexers in the I/O drawer. The InfiniBand multiplexers are used to interconnect servers, communication infrastructure equipment, storage, and embedded systems. In addition to using InfiniBand to interconnect systems, all of which use InfiniBand, the InfiniBand multiplexer supports other I/O technologies such as Ethernet connection provided by 1 gigabit and 10 gigabit connections to a variety of devices that support this popular local area network technology. One noteworthy use of Ethernet is to construct large server farms, particularly to interconnect blade servers with each other and with other mainframes. The PCIe connections from the processor book to the other I/O drawers are via PCIe fan-out to PCIe switches. The PCIe switches can connect to a number of I/O device controllers. Typical examples for Z13 are 1 gigabit per second and 10 gigabit per second Ethernet fiber channels and OSA express controllers. OSA is an I/O adapter technology that provides stream high-speed transfers between system memory and a high-speed network interface such as Ethernet. So fairly complicated, kind of on the extreme side here, but maybe in the context of letting you see the whole dimensions and array of input and output, that might be a nice way to be finishing up this chapter. So we spent a lot of time talking about a variety of different input and output strategies, external devices, I/O modules, programmed I/O, interrupt-driven I/O, direct memory I/O, and DDIO was also another thing that we had a chance to be talking about. Direct cache access, I/O channels and processors, and then talking about the external interconnects for standards. Most recent one that has been quite useful for me is Thunderbolt, but USB is definitely a mainstay, Ethernet, Wi-Fi, all of that. And then we got a chance to be talking at an extreme IBM level of a server, the IBM Z Enterprise C EC12 I/O structure. All right, well, thank you very much. That's going to finish it up for this lecture.